The beautiful things about mathematics is that the more of it that you learn, the less of it you need to remember. Which sounds weird to say, but I think, is that your experience kind of as a math major?
Yeah, eventually kind of becomes just hardwired in your brain.
It becomes hardwired because what you find out is that you don't need to know the names of each individual tree in the forest. You just need to know the forest, right? And so one of the goals of today is to underline the fact that we can take what we learned about how to solve equations with fractions, and we can transport it directly into a strategy for solving inequalities with fractions, because there's no overall difference in the strategy, with one small potential wrinkle that we talked about last time we worried about inequalities. So let's take a look. This is 3A8, so this is on page 82. I think it's 82. And the goal for this problem is just to solve this inequality for x. So based on what we did with equations, what would you think is a good first step to use in a strategy for solving this inequality? What's my step one?
Find the lowest common denominator.
Yeah. What is the lowest common denominator for the fractions that are present in this inequality? Well, what do you think?
18.
18 works. Yeah. 18 is both a multiple of 9 and it's a multiple of 6. There are, of course, bigger numbers that also would work. 18 happens to be the smallest, so that's the lowest common denominator. Okay, so now that we know that this lowest common denominator is 18, what do I want to do with that 18?
Multiply by it.
Yeah, multiply through by it. Multiply both sides. This is the magic step, right? This is the step that's going to kill all of the fractions in one swoop. It's like a broadsword, just cutting them all down like reeds. So we're going to multiply both sides by 18, and all the fractions are going to fall, right? 18 times everything. Okay, so now is when the arithmetic comes in, the fraction arithmetic. And fortunately, again, it's only fraction multiplication. There's no fraction addition or subtraction, so we don't need common denominators. There's no fraction division, so we don't have to flip and multiply or anything. All we have to do is multiply across, 18 times each one of these coefficients. And again, I'm going to try to do this in the efficient way that we talked about, where if I'm going to multiply 18 times negative 5/9, what's the quick way to do that?
I
Put
put 18 divided by 9.
the 18 divided by 9.
You get the result and times it by 5.
Yeah, exactly. What this really is 18 over 9 times negative 5 over 1, right? And 18 over 9 is 2. 2 times negative 5 gives us negative 10. And so that first term becomes negative 10x. My second term, 18 times negative 2, will give me negative 36. Then for my third multiplication, 18 times 7 over 6. What's the efficient way there?
5 by 6, 3.
Yeah, divide the 18 by 6 and multiply it by 7 over 1. 18 over 6 becomes,
3 over 1.
yep, and 7 over 1 is 7. 3 times 7?
21.
21. That has an x on it. And then 18 times 4 over 9. The 18 over 9 turns into 2. I'm going to again write that in here. 18 over 9 times 4 over 1. 18 over 9 is 2. 4 over 1 is 4. And 2 times 4 is 8. Cool. So now all our denominators are gone. We have no more fractions. We only have whole numbers. That's the magic of clearing denominators. So now it's just a matter of employing the rest of our strategy. Get all variables to one side, which always happens by an addition or a subtraction. And then we just have to unwrap using the reverse order of operations, SADMAP. Okay, so what does getting all the variables to one side look like in this example? What's my step? How do I get all the x's to be on the same side of the equation? Jerry?
Subtract 21.
Subtract 21x. Again, I'm following kind of my left-right bias here, where I like to have all my variables on the left and all my constants on the right. So if that's my bias, then I'm going to subtract 21x from both sides. What's negative 10x minus 21x going to be? Negative 31x, right. So we still have to do some addition and subtraction of numbers with mixed signs, right? That's never going to really fully go away. So I get negative 31x on the left-hand side. Yeah, why don't I just leave it at that? So it's negative 31x minus 36, less than or equal to 8. Okay, then what comes next? Add 36, right. So we moved all of our variables. Now it's time to start the unwrapping process by reversing the order of operations. So do all of our subtraction and addition that we can do until there's none left. That involves adding 36 to both sides, getting negative 31x less than or equal to 44. And then finally, what's my last step? Divide by negative 31. So on the right-hand side of my inequality, I end up with the number 44 divided by negative 31, which is more conventional to move that negative sign into the numerator rather than the denominator. So as long as it's only in one of the two parts of the fraction, we're okay. My left-hand side is just x, and my inequality sign is, what goes here? The same? Why? So we're just trying to decide now what to put, what inequality symbol belongs here in my final answer. How do we decide? This is the one wrinkle that separates solving equations from inequalities. We divided it by a negative. Right. This division that happened here at the very last step, this was division by a negative quantity. So what happens when we divide both sides of an inequality by a negative quantity? Yeah, we end up needing to reverse the sense of the inequality. So that's the one big difference. It's not that big of a difference because it doesn't always happen, right? We don't always have to divide by a negative in the process of solving an inequality, but when we do, we have to flip the sign, divided by a negative. So that means flip the inequality. Flip the script. So this is no longer less than or equal to. Now it needs to be greater than or equal to. So when I say that the same strategy that works for solving an equation works for solving an inequality, this is the only exception to that. Right? This is the only extra consideration that needs to be in your mind when you're solving an inequality. If at any point you have multiplied or divided both sides of this inequality by a negative quantity, that inequality sign needs to flip. But that's the only time when a step in this process is different than it otherwise would be for solving an equation. Because the thing about an equal sign is if you flip it, it's still just an equal sign. So equal signs don't care if you multiply or divide by a negative. They just flip into other equal signs that are all the same. Inequalities do care. Because of the ordering on the number line gets reversed when we multiply or divide the number line by a negative. Right? And so our whole compass gets turned around. Our GPS that used to be pointing east is now pointing west after we multiply or divide by a negative, so we have to flip the sign. So we just finished solving an inequality, and the answer that we got is shown right here. X is greater than or equal to negative 44 over 31. So if you recall, last time we talked about inequalities, we talked about how to draw a picture that conveys that information using a number line. So what I have here on the screen is a little view of the real number line, right? I've labeled a few points on it, 0, 5, and 10. And the point, negative 44 over 31, is right about here. It's negative 1 point something. Right? So if I'm going to draw a picture that corresponds to this solution, how would I shade in this number line? First of all, this image is already kind of doing it for us. It's shaded everything on this side. How do we know, by the way, that we would shade everything to the right instead of the left of negative 44 over 31? Because it's greater than or equal to, right. And greater than means to the right on the number line. So we know we're going to shade everything to the right. But I want to add one more thing to this picture that conveys the fact that this inequality is greater than or equal to, and not strictly greater than. What can I add to this picture that reinforces that information?
Solid dot.
Yeah, exactly. Let's add to it a solid dot. In other words, a filled-in circle at negative 44 over 31. So now we have a nice visualization that shows us not only that all the numbers greater than negative 44 over 31 are included in my answer, but so too is the number negative 44 over 31 itself. It's included because we filled in that circle to reinforce the point. Now, here's the next thing I want to do with that. Is that now that we have this picture, let's also talk about a way of writing this answer using what's called interval notation. So this is a way to express this picture in yet another way. In interval notation, what we do is we express a set, a subset, an interval, I should say, of the real line, using its leftmost endpoint and its rightmost endpoint, as well as some notation to indicate whether those endpoints are included or not. So these are the four things that make up interval notation: a left endpoint, a right endpoint, and then we also need what I'm going to call a left inclusion symbol that tells us whether that endpoint is part of the solution or not. And we also need a right inclusion symbol. Is the right endpoint included or not? Sorry, I'm running off the side of the screen here. So to make interval notation, we need to include these four things. And then in the middle of these four things goes a big old comma. So my first question is, in our solution set, what is the leftmost endpoint? What is the least number that belongs to this solution set? Yeah, that's staring at us in the face. Right? Negative 44 over 31 is the leftmost number that belongs to our solution set. What's the rightmost endpoint? What's the largest number that's included in our solution set? How high up does this go? That sounds like Watergate conspiracy or something. How high up does this go? How high up does this solution set go? How far to the right on the number line? Infinitely far, exactly, right. So we just need to put a symbol here that indicates that this has no end. It goes all the way out to the horizon on the real number line to the right. So we do use the symbol for infinity, right? Which is an 8 on its side, like this, right? And if we want to be really fancy, sometimes we'll also decorate it with a plus sign in front of it to indicate it's positive infinity. It's the right side of the real number line as opposed to the left side. We don't have to put that there if we don't want to, but sometimes we'll put it there for emphasis. Okay, so we've identified the left endpoint, we've identified the right endpoint. Now we need to add to this notation that tells us whether those endpoints are actually part of the solution or not. Is negative 44 over 31 actually a part of this set?
Yes.
Yes, we know that because it's greater than or equal to, right? X is greater than or equal to negative 44 or 31. So we decided to include this point and put a solid dot in it. And so for our inclusion symbol on the left-hand side, we want to choose a symbol that indicates that that number is included. And so for that, we choose a square bracket. So one thing that you'll notice as you work more with interval notation is that these three symbols tend to go together. A greater than or equal to sign, a solid dot, and a bracket, because they are all indicative of the same inclusive inequality. It not only includes everything which is greater than, but it also includes what is equal to. So those three are kind of they're a triad, they're a matched triplet, so they come together. Whenever you see a greater than or equal to sign in your inequality, expect to see a solid dot in your graph, and expect to see a square bracket in your interval notation. Conversely, what about infinity? Is infinity actually a part of our solution? Does infinity satisfy this inequality? Well, here's the slippery thing about infinity. It's not actually a number. Infinity is not something we can actually plug in for x anywhere and get meaningful stuff, because infinity doesn't have arithmetic that connects it with the real number system in any meaningful way, at least not in our class. So we will never count infinity as part of our solution set because it's not a number, and our solution set consists only of numbers. So infinity, anytime we see it, is never going to be included in our answer. And for that reason, we're going to use the other kind of inclusion symbol that indicates not included. That's a round bracket. Another way to think about this is I could write this in the following way. I could say that all the x's which satisfy this inequality are, on the one hand, greater than or equal to negative 44 over 31. But on the other hand, how do they compare to infinity? Well, they're going to always be less than infinity, right? And never equal, because we're never going to let x equal infinity, because infinity is not a number. Right? And so in that example, we can kind of see how when we have a less than sign, that tends to be accompanied by round brackets, indicating not included. So that's kind of the meaning of these two symbols at the end. These symbols indicate, yes, is included. Whereas the symbols over here on this side indicate not included. And so the interval notation that we could use to express the solution of this inequality is the interval from negative 44 over 31 to positive infinity, inclusive of the former, but exclusive of the latter.